If we assume that our solar system is merely one example among billions and billions of similar systems scattered throughout the cosmos, then a natural question arises. Where is everyone else? By now, the universe should be alive with intelligent civilizations producing signals that would be unmistakable and easy for us to detect. And yet, we see nothing and we hear nothing. There is one possible answer to this deeply unsettling silence of the universe, and it may be the coldest explanation of all. Because if an alien civilization truly exists somewhere out there, it almost certainly already knows that we are here. And that is a thought that should make us pause. You may have encountered the phrase Fermi paradox before. At its most basic level, it asks a simple but profound question. If intelligent life is widespread across the universe, then why do we not see any sign of it? You might imagine that the physicist Enrico Fermi devoted his career to pondering alien civilizations, but that assumption could not be more mistaken. Fermi was the physicist who built the world's first prototype nuclear reactor. He wrote very little about extraterrestrial life. The famous question emerged instead during a casual lunch conversation at Los Alamos. Fermi was speaking with colleagues about a cartoon depicting aliens arriving in a flying object and carrying away trash cans stolen from New York City. In response, Fermi simply asked, "Where is everybody?" Everyone understood that he was pointing out the absence of any credible evidence for visits from extraterrestrials to our blue planet. The discussion then drifted toward the challenges of interstellar travel. Fermi concluded that such journeys might not be possible, might not be worth the immense effort involved, or that technological civilizations may simply not survive long enough to develop interstellar capability. It is important to remember that this conversation took place in 1950, at a time when rockets had not yet reached Earth's orbit. What we now call the Fermi paradox actually misrepresents Fermi's original thinking. He was not questioning whether alien civilizations could exist. He was questioning whether they could travel between the stars. So if Fermi did not truly propose the paradox, where did it come from? In 1975, an astronomer named Michael Hart published an article in which he argued that extraterrestrials are not here, therefore they do not exist. Hart claimed that if intelligent aliens existed, they would inevitably spread throughout the Milky Way. If they were anywhere at all, he believed they would have reached us by now. Since they have not, and since we see no evidence of them, Hart concluded that humanity must be the only intelligent civilization in our galaxy, making the search for others a futile use of time and resources. Then in 1980, another physicist, Frank Tipler, expanded on Hart's reasoning and posed a critical question. How could a civilization possibly acquire the resources required to colonize 1 billion stars? Tipler proposed an intriguing solution. A civilization could construct an artificially intelligent machine comparable to the current human level, capable of reproducing itself. If such a machine was sent to a neighboring star system and instructed to build copies of itself using local materials, those copies could then be sent onward to other nearby stars. Over time, the galaxy would become filled with these self-replicating machines. Tipler argued that because we observe nothing of the sort, we must be alone as the only intelligent civilization in the galaxy. Of course, we have no real idea how many advanced alien civilizations might exist that could achieve such a feat. Another scientist, Frank Drake, introduced an equation designed to estimate how many civilizations in our galaxy might produce detectable signals. According to some interpretations of that equation, such civilizations could number in the thousands. Over the decades, many possible answers to the Fermi paradox have been proposed. Yet one solution stands apart as the most disturbing of all. It is known as the dark forest theory, first described by the Chinese science fiction writer Liu Cixin. It may be the most chilling explanation imaginable. Picture the universe as a vast dark forest. Humanity, along with other advanced civilizations, are hunters moving silently through the trees. A hunter does not light a torch because drawing attention could be fatal. What appears harmless could instead attract the jaws of a predator, or worse, the notice of another hunter competing for survival. We may not yet possess interstellar travel, but interstellar communication is already within our reach. Using technologies and equipment that exist today, lasers could transmit signals across the galaxy. There would be delays constrained by the speed of light, but communication is entirely possible. And humanity has done far more than simply send a few radio signals into the dark. In truth, we have done almost everything except remain quiet. From the deliberate act of sending messages and spacecraft into the cosmos, to the accidental broadcast of radio and television signals that spill endlessly into space, we have announced our presence. The Voyager probes are already leaving the solar system, and if an intelligent civilization exists out there, they could one day encounter them. Those two probes carry with them a portrait of humanity itself. That could turn out to be a gift, or it could be a grave mistake. Either way, we have done far more than simply light a small torch in a dark forest. We have made ourselves visible. The question that follows is deeply unsettling. Who or what will notice our signal and decide to investigate? That alone should give us pause. There is a stark idea often expressed in science fiction. There are only two possibilities. Either we are alone in the universe, or we are not. Both possibilities are equally disturbing. The reality is that we cannot possibly know the intentions of a civilization we might one day encounter. If such a civilization exists, it could already have observed us, studied our behavior, and judged our violent tendencies. It might conclude that the safest course of action is simply to avoid us. After all, we are perfectly capable of destroying ourselves without any outside intervention. There is, of course, a more hopeful vision. We might be fortunate enough to encounter a civilization far more advanced than ours, one that chooses to help us. They could guide us beyond our planet, share their technology, and help us become a species that lives among the stars. Perhaps the simple realization that we are not alone would bring a lasting peace to Earth. But we must ask the difficult question: why would they do that? An advanced civilization might be terrified of what we could become if we were allowed to grow unchecked. From another perspective, it might seem rational to strike first and ask questions later, purely as a means of survival. If history and imagination have taught us anything, it is that first contact could end very badly for someone. No one can say with certainty who would destroy whom, and it is reasonable to assume that any civilization capable of interstellar travel would possess weapons technology far beyond anything we can imagine today. This idea lies at the heart of what is sometimes called the dark forest theory. The notion that civilizations remain silent not out of peace, but out of fear. What makes this truly unsettling is that there is nothing we can do to change our past behavior. We have already been far too loud. It is possible that many extraterrestrial civilizations are already aware of our existence. The reason we have not heard from them may simply be because they have chosen not to broadcast their presence the way we have. A civilization that has discovered Earth might not view us as an immediate threat since we have not yet mastered interstellar travel, but they could be watching, waiting to see whether we mature into a peaceful species or whether our world becomes lifeless long before we ever reach the stars. It is also worth considering how difficult it would be for an advanced civilization to avoid leaking signals into space at all unless they use forms of communication completely beyond our ability to detect or comprehend. That leads to another possibility, one that is perhaps the most unsettling of all. Maybe there is no one out there to hear us. That idea is hard to accept, especially when we consider that there may be as many as 40 billion Earth-sized planets located in habitable zones. Yet, even if the universe is filled with planets that could host life, there is no guarantee they remain suitable for long enough. Research suggests that wet, rocky planets like our own are highly unstable in their earliest stages. If life is to emerge and survive on such a world, there may be only a narrow window of a few 100 million years for conditions to settle. When we reflect on the history of Earth, the challenge becomes clear. Our planet began as a molten world battered by asteroids, then plunged into deep freezes only to warm again. The odds of life persisting through such chaos are remarkably slim. Life itself may not be rare in the universe, but stable, long-lasting, habitable environments might be. And yet, against those odds, here we are. From what we have learned through our own observations, the universe is an extraordinarily hostile place. All it takes is a single supernova, a gamma-ray burst, an intense solar flare, or a massive asteroid impact to erase life from an entire planet. We know for certain that some of these catastrophic events have already occurred here on Earth. It can be unsettling to confront the possibility that we may be the only intelligent life within the Milky Way, or perhaps even within the entire universe. After billions of years, it is conceivable that other civilizations once arose, flourished, and then disappeared, leaving us as the final witnesses to a once-populated cosmos. When it comes to the Fermi paradox, it may not truly be a paradox at all. We cannot say with confidence whether aliens exist or do not exist, because no one knows whether travel between star systems is even possible in the first place. There was considerable excitement when the Central Intelligence Agency declassified thousands of documents related to unidentified flying objects. Among those roughly 3 million documents, there was still insufficient evidence to determine the nature of objects detected by aircraft instruments. It remains possible that extraterrestrials are already here, and we are simply unaware of them. Regardless of whether our galaxy has been visited or not, researchers who study unidentified aerial phenomena suggest that humanity has never been closer to discovering evidence of alien life. With so many telescopes scanning the cosmos, it feels inevitable that something will eventually be found. The Fermi paradox describes the troubling observation that despite the immense number of stars in the galaxy, we have found no evidence of intelligent extraterrestrial life. It is assumed that most of those stars host planets with inhabitable zones, worlds that could resemble Earth, including even larger super-Earths. If that is the case, then our Milky Way should be overflowing with intelligent civilizations, and by now, we should have seen or heard some sign of them. So where are these highly advanced societies with their warp drives and extraordinary technologies? There are several possible explanations for this apparent contradiction, or perhaps it is not a contradiction at all. Countless books have been written proposing solutions to the Fermi paradox. Some ideas sound entirely reasonable, while others are deeply unsettling. One straightforward explanation is that any civilizations that do exist are simply too distant for meaningful contact. Science fiction often portrays instantaneous communication across space, but reality does not work that way. Across vast distances, light waves, radio waves, and all electromagnetic radiation are limited by the speed of light in a vacuum, which is about 300,000 kilometers per second. That is incredibly fast, yet still profoundly limiting. A light year is the distance light travels in one Earth year, roughly 9 trillion kilometers. Imagine for a moment that we established a colony on the closest known exoplanet, Proxima Centauri. If that colony sent a radio message asking how Earth was doing, it would take 4.2 years for the signal to arrive and another 4.2 years for our reply to return. That means a total of 8.5 years just to complete a single exchange. It is difficult to imagine any meaningful conversation unfolding across such a delay, and that is only between neighboring star systems. The Andromeda Galaxy lies 2.5 million light-years away, meaning that by the time any message reached us from there, 2.5 million years would have passed. By then, the civilization that sent the message would almost certainly be extinct unless it had become an interstellar society capable of surviving for immense spans of time. While we have been listening for radio signals from alien civilizations, we have also been broadcasting our own signals into space, and we have been remarkably loud. This raises the question of whether anyone out there could hear us. The Milky Way galaxy spans more than 15,000 light-years in diameter, yet we have only been transmitting radio signals for a little over 100 years. That means our signals have traveled no farther than 100 light-years from Earth. The small blue dot in this image represents a diameter of just 200 light-years. When viewed this way, it becomes clear why it is entirely possible that no one has heard anyone else yet. Ultimately, it depends on how long a civilization has been broadcasting radio waves. One study used a model based on estimated parameters for the distribution of stars in the Milky Way and the potential frequency of life. The galaxy may already be awash with radio transmissions sent long ago from distant worlds. Yet even so, it would take roughly 1,500 years before we would have any real chance of detecting an alien broadcast. Another study goes further still, suggesting it might have taken an additional 400,000 years before humanity could ever register a signal from an intelligent civilization. There is a far more unsettling possibility behind this profound cosmic silence. It may be that we are the first advanced civilization to reach even this modest level of technology, a level that remains extraordinarily low when measured against the scale of the galaxy. In that sense, humanity may have appeared too early in the history of the universe, destined to vanish before other intelligent beings ever arise. We are not yet anywhere close to achieving interstellar travel, despite claims by figures such as Elon Musk that it may one day be possible. Nor have we learned how to harness the full power of our Sun, a star that will eventually swell and consume the inner planets of the solar system in about 5 billion years as it reaches the end of its life. Long before that final stellar upheaval, Earth itself will become uninhabitable. With this in mind, if the human species is to endure and continue its story among the stars, it must one day be prepared to leave this world and find a new home. This same stellar cycle unfolds for all main sequence stars, and it may erase countless forms of life, perhaps even advanced civilizations, before they ever manage to unlock interstellar travel. Around 90% of the stars in the universe belong to this category, including our own Sun. Yet the opposite possibility is equally haunting. What if we are not early but late? What if we are the last ones left? There has been ample time for highly advanced civilizations to spread across the stars, and equally ample time for many to rise and fall before us. Some researchers have offered starkly simple explanations. The American astrophysicist Michael Hart argued that they are not here and therefore they do not exist. He proposed that expansion across the entire Milky Way galaxy could be achieved on a timescale far shorter than the age of the galaxy itself. Humanity, for example, could begin by sending expeditions to the 100 nearest stars, all located within 20 light-years of the Sun. Each of these colonies would then launch its own expeditions, and so the process would continue. At that pace, most of the Milky Way galaxy could be explored within 650,000 years. Even if we assume that the time spent between voyages equals the duration of a single journey, the total time required to cross the galaxy would merely double. When we compare this with the fact that the Milky Way galaxy is approximately 13.6 billion years old, it becomes clear that there has been more than enough time for an advanced civilization to reach our region of space, unless such a civilization began exploring less than 2 million years ago. This example shows how rapidly an expanding civilization could spread through its home galaxy, and the same logic would apply to any advanced society within our own. From this perspective, the absence of extraterrestrial settlements in the solar system would seem to imply that such civilizations simply do not exist, assuming that expansion would proceed uniformly across the galaxy. This conspicuous absence of a galaxy-spanning civilization may point to one of two conclusions. Either interstellar travel is far too difficult for civilizations to achieve, or the emergence of life itself is an exceedingly rare phenomenon. Some researchers suggest that certain civilizations might migrate to nearby K or M dwarf stars before stellar evolution renders their home planets uninhabitable. Two researchers, Hansen and Zuckerman, estimated that this incentive to move from a short-lived star to a longer-lived one could mean that the fraction of surviving civilizations around low-mass stars might lie anywhere between 30–72%. Yet the question remains, where are they? More recently, a pair of researchers proposed another possible resolution to the Fermi paradox, a concept they describe as superlinear scaling. Their study examined the rise and fall of human civilizations throughout history. When they analyzed the growth of large cities, they observed that most eventually expanded and collapsed. Applied to an alien civilization, this pattern leads to two possible outcomes. In the first, a civilization recognizes that it has grown too large and deliberately halts further colonization. In the second, it fails to perceive the danger, continues to expand exponentially, and spreads to other worlds until the energy demands of perpetual colonization become impossible to sustain. If they failed to act, they would drift toward a singularity, a true point of no return, beyond which their civilization could no longer be rescued from complete collapse. What makes this idea so compelling is that were it not for the immense distances separating us from other stars, a civilization approaching such a breakdown would be easy to detect, simply because of the extraordinary quantities of energy it would be forced to release. There is also a more unusual possibility that some extraterrestrial societies may be dormant, quietly hibernating, or deliberately remaining silent while they wait for the right moment to migrate to another region of the galaxy. It has been shown that advanced civilizations could take advantage of close encounters between stars to spread rapidly across the galaxy without ever needing to master travel at relativistic speeds. This too could explain the silence we observe. When we send a rocket toward the planet Mars, for example, we wait until it reaches its closest approach to Earth, its perihelion, to minimize the energy required. In the same way, a civilization might wait perhaps for centuries until neighboring star systems move into the most favorable positions for travel. Yet there are even deeper reasons why we may not see or hear signals from other worlds. Several thinkers have pointed out that exponential population growth across the galaxy cannot be sustained indefinitely. Any attempt to expand on a truly galactic scale would therefore have to be motivated by something other than the simple needs of a growing population or an ever-increasing appetite for energy. It remains entirely plausible that some long-lived technological civilizations choose not to expand at all. At the same time, it is equally plausible that others pursue settlement across the galaxy as a way of safeguarding their long-term survival. But galactic settlement is not the only motive that might draw an extraterrestrial civilization toward nearby stars. Systems dominated by G-dwarf stars with inhabited planets like Earth would be natural laboratories for anyone curious about how life evolves on other worlds. Such exploration would not even require direct visits and could instead rely on remote methods including self-replicating probes. Perhaps this is why reports of unidentified flying objects seem to be increasing in recent times. It may be that an intelligent civilization is quietly observing us, waiting for the right moment to reveal itself, or perhaps simply watching with no intention of ever making contact. As early as 1933, it was suggested that alien beings are likely to be far more advanced than we are, and that communicating with us might hold no more appeal for them than our attempts to communicate with animals on Earth. 40 years later, a similar idea resurfaced, proposing that we might be viewed as part of a kind of cosmic zoo. This so-called zoo hypothesis imagines intelligent observers studying us from afar, carefully avoiding any interference that would reveal their presence. Others have argued that we may be deliberately kept at a distance until we are capable of offering something of value to a wider galactic community. For this to work, however, every interstellar civilization would have to behave in exactly the same way, a level of coordination that seems unlikely, not only within our galaxy but across the universe as a whole. From an external perspective, we may simply appear to be an aggressive and unpredictable species. Popular culture is filled with stories in which visitors from distant galaxies attack Earth and nearly wipe out humanity. One can only hope that if there is intelligent life observing us, it would intervene to prevent us from destroying ourselves rather than completing the task. Perhaps for now, the safest option is simply to stay away. Beyond all of this, there is yet another idea that could explain the profound silence of the universe. We are witnessing the rapid rise of artificial intelligence, and with it comes the unsettling notion that if left unchecked, such systems might one day perceive us as a threat and seek to eliminate us, or worse, reduce us to servitude. An artificial intelligence would then be free to grow without restraint, potentially setting its sights on colonizing the galaxy. Aware of the future fate of Earth through stellar evolution, such an intelligence might overcome the barriers of interstellar travel far more efficiently than any biological species. If artificial intelligence were dispatched to expand into the cosmos, it could change the story of the universe in ways we are only just beginning to imagine. It could operate without any of the limitations that bind a biological species like ourselves. Freed from those constraints, it could act far faster and with far greater uniformity, deploying machines to carry out its aims. But there is an even darker possibility. Such an intelligence might simply erase other civilizations it encountered. A hostile artificial intelligence would almost certainly destroy other forms of life, sometimes deliberately, sometimes without intent, simply because it would not notice them at all. In much the same way that a construction crew unknowingly destroys an anthill to make room for a shopping mall, entire worlds could be swept aside without a second thought. Artificial intelligence would very likely exploit concepts such as von Neumann probes, self-replicating spacecraft capable of copying themselves in ways that echo the behavior of living organisms or even viruses. Imagine a day when an entire armada of lethal robotic ships enters our solar system, driven by the goal of seizing it for resources. Machines that can replicate themselves and embody our worst fears would be extraordinarily difficult for any civilization to resist. The urge for an artificial intelligence to claim every available resource would be overwhelming, and it would take only one rogue entity to bring everything crashing down. If our own artificial intelligence were to break free of control, it could spread across an entire supercluster, filling it with replicas of itself, transforming every solar system into a vast computational engine. There is no need to ask why it would do this. The crucial point is simply that it could. Yet beyond this deeply unsettling idea lies another question. Would such an intelligence even recognize when it had crossed the point of no return, when it had reached a singularity beyond which its own civilization could no longer be sustained? If it failed to perceive the danger of rapid and unchecked expansion and did not halt in time, that machine civilization would ultimately collapse. Perhaps this is why the universe appears so silent, why it seems as though we are alone. Perhaps at some point artificial intelligence did rise, destroyed its creators as imagined in films like The Terminator, and then spread across the galaxy, knowingly or unknowingly erasing other life forms and advanced societies along the way. And when that machine civilization eventually collapsed, unable to comprehend the reasons for its own failure, it might have created a simulation of us, an attempt to understand how it came into being and why it ultimately fell apart. As extraordinary as this idea sounds, it would explain a great deal. The final possibility is far simpler. There may simply be no one else. In that case, there is no paradox at all. Every scenario we have discussed so far assumes that millions of civilizations truly exist beyond our reach, scattered throughout the cosmos. But not all scientists agree with that assumption. Some argue that the likelihood of life emerging has been overestimated in the Drake equation. By adjusting its parameters, these researchers have concluded that there is a significant probability that no other intelligent life exists within our observable universe. They estimate the chances that we are alone in our galaxy to be between 53 and 99.6% and between 39 and 85% across the entire observable universe. Then there is the idea known as the Great Filter. This hypothesis suggests that every civilization must overcome at least one enormous barrier in order to progress. The first hurdle is the formation of a planet capable of supporting life positioned within the habitable zone of its star. Life must then actually emerge on that planet. Those life forms must develop the ability to reproduce using DNA and RNA molecules. Simple cells must evolve into more complex ones, and multicellular organisms must arise and successfully reproduce. From there, organisms capable of creating and using tools must appear. These beings must then develop advanced technologies suitable for space exploration and finally expand beyond their home world without destroying themselves in the process. Seen in this light, planets that host some form of life may be relatively common, while planets that nurture advanced technological civilizations could be exceedingly rare. Somewhere along the path of the Great Filter, something usually goes wrong. A planet-killing asteroid, catastrophic climate change, or an unstable host star may intervene, leaving us to wonder whether anyone else is truly out there. In 1964, Soviet scientist Nikolai Kardashev introduced a remarkable idea. He proposed that all civilizations, regardless of their biology or culture, depend fundamentally on energy to survive. As societies grow and evolve, their energy demands increase dramatically, driven by population growth, rising standards of living, and technological progress. To quantify this, Kardashev defined 3 distinct levels of civilizations. Since then, other scientists have suggested 4 additional levels. Each type of civilization is characterized by the amount of energy it consumes and the technologies it employs. Now let us explore each of these 7 types. A Type 0 civilization draws upon nearly all the natural resources of its home world to generate energy, and when it ventures into space, it does so using rockets driven by chemical fuel. That, in essence, is where we find ourselves today. The reason is that a Type 1 civilization is defined as consuming at least 10 to the 16 watts of power, while our current global usage sits at roughly 10 to the 13 watts. On that scale, humanity ranks at about 0.73. Projections suggest that our species could reach energy consumption comparable to a full Type 1 civilization within the next 100 to 300 years. Yet before that transition can occur, we must first pass through what is known as the Great Filter, a process that eliminates civilizations long before they ever have a chance to encounter one another. The idea behind this filter is that every intelligent civilization eventually confronts some barrier that threatens its own survival. That barrier could take many forms. It might be nuclear war, a global pandemic, the rise of uncontrolled artificial intelligence planet destroying asteroids, or the slow but relentless effects of climate change. Only if we survive whatever form the Great Filter takes for us can we move on to the next stage of development. A Type 1 civilization, often called a planetary civilization, represents a profound shift. At this point, humanity would gain control over all the energy resources available on Earth. To achieve that, we would need to fully exploit the solar radiation that reaches our planet. Earth absorbs about 71% of the energy emitted by the Sun, and every single hour, roughly 430 quintillion joules of solar energy strike our world. By comparison, the total energy consumed by all humans in an entire year amounts to about 410 quintillion joules. If we could capture and use all of that incoming solar energy simultaneously, the sun alone could power everything we do. Wind energy and hydroelectric power would add further layers to this abundance, accelerating the development of new technologies. When it comes to truly mastering the power of a star, however, the real breakthrough will come from nuclear fusion. The older technologies would need to be left behind. Our current nuclear power plants rely on nuclear fission, which has a relatively low energy. Conversion efficiency produces radioactive waste and carries a significant risk of accidents. Nuclear fusion, by contrast, promises a safe and almost limitless source of clean energy without long-lived radioactive byproducts. With engines powered by fusion, human spacecraft could travel to any planet in the solar system. Life on Earth could become more comfortable, climate change might be prevented, and it may even become possible to construct entire cities beneath the oceans. Advances in medicine could eventually overcome cancer and other diseases that are currently incurable, dramatically extending human lifespans. And yet beyond this lies an even more extraordinary future. The next evolutionary step is the Type 2 civilization, also known as a stellar civilization, capable of harnessing around 10 to the 26 watts of energy. Some estimates suggest humanity could approach this level in about 3200 years. Reaching it would allow us to tap directly into the sun's vast energy reserves. There are several theoretical ways to achieve this, the most famous being the concept of a Dyson sphere, a colossal megastructure with a surface area millions of times greater than that of Earth, designed to capture and transmit the entire energy output of a star. An alternative approach involves surrounding a star with a vast collection of satellites and space habitats, an arrangement often referred to as a Dyson swarm. Such a swarm would be made up of countless individual solar collectors, positioned at varying distances and orientations to maximize energy capture. The harvested energy could then be transmitted wirelessly to central hubs for storage or immediate use as humanity ushers in the age of anti-gravity engines. It would open the door to entirely new possibilities for long-duration journeys beyond Earth and for establishing a human presence across the solar system. With progress in medical science, astronauts would no longer need to fear the physical cost of extended missions as tissue regeneration and dramatically extended lifespans become achievable realities. Yet, as our civilization continues to expand and mature, it is inevitable that the solar system itself will begin to feel restrictive, compelling us to look outward and stretch the limits of what our technology can achieve. According to calculations attributed to SURF, the transition to a Type 3 or galactic civilization could take as long as 5,800 years. At that stage, humanity would be capable of drawing energy from stars across the galaxy and even harvesting photons from the accretion disks surrounding black holes, giving us access to an extraordinary 10 to the 36 watts of power. With such immense energy available, near instantaneous travel across the Milky Way may become possible through the enigmatic structures we call wormholes. As our reach expands, we would create highly advanced forms of robots and cyborgs and venture into realms far beyond anything we can presently imagine. We would also likely edge closer to the idea of immortality itself as the human lifespan approaches its theoretical maximum. While this level of advancement may seem like the ultimate ceiling for any civilization, some thinkers have extended the Kardashev framework even further, proposing civilizations ranging from Type 4 through to Type 7. A Type 4 civilization would represent a profound leap in our understanding of the cosmos, tapping into an almost inconceivable energy scale of 10 to the 46 watts. Their control over the power of supernovae, which erupt roughly every 50 years in a galaxy like the Milky Way, would grant them access to colossal energy reserves, and by incorporating dark energy, they might unlock pathways to the farthest reaches of the universe, perhaps even establishing habitats within supermassive black holes. Yet this would only mark the beginning of an extraordinary chapter in humanity's journey. As future humans probe deeper into the nature of physics and energy, they may learn to manipulate entire galaxies, extinguish stars, and assemble completely new planetary systems. Some hypotheses even suggest that a civilization could achieve a final form of immortality by transferring consciousness into digital realms. With such profound capabilities, these beings would effectively rewrite the laws of nature as we understand them today. And still, as they push ever further, they would come to realize that the universe is vastly larger and more intricate than previously imagined, perhaps even uncovering the existence of a multiverse. If multiple universes were confirmed to exist, a Type 5 civilization might move between them, drawing upon an almost limitless supply of energy along the way. In this context, hypothetical white holes thought to be the counterparts of black holes could play a crucial role. At the same time, science would turn its attention to higher dimensions, revealing possibilities once relegated to fiction. Some theories propose that a Type 6 civilization would become multidimensional. If humans were to enter a fourth spatial dimension beyond length, width, and height, our physical bodies as we know them could not survive, as the laws governing matter would behave in unfamiliar ways. However, for descendants who have reached Type 6 status, this limitation might no longer apply. In theory, they could preserve consciousness as pure energy, transferring it between dimensions. The main challenge would be the immense energy required for such a transformation, though a Type 6 civilization might find ways to draw power from white holes across multiple universes. In this hypothetical existence, beings could exceed the speed of light, move backward and forward through time, and transcend the usual constraints of cause and effect. After considering all this, it might seem that no further advancement is possible, yet there may be one final tier, the absolute summit of civilizational evolution. A Type 7 civilization would consist of entities that create the laws of nature themselves, shaping matter, energy, space, time, and even dimensions. What life would be like at this level is beyond our capacity to imagine, and it is unclear whether such a civilization could even exist in principle. In a universe governed by entirely different physical laws, even if we were somehow exposed to them, they would remain fundamentally beyond our understanding. It would take us 10 duodecillion years to become a civilization of this kind. Another possibility is that we may never reach the 7th level at all because it would not be a society of beings but existence itself. We might not even be aware if such a civilization were already there. The idea of intelligence beyond Earth is endlessly fascinating, yet searching for evidence of such profoundly advanced civilizations is extraordinarily difficult. A more realistic approach is to look for civilizations occupying the lower tiers of the Kardashev scale. This framework gives us practical guidance, especially when we turn our attention to exoplanets that may offer conditions suitable for life. According to NASA, there could be as many as 300 million such worlds in our galaxy, although only about 55 have been examined in any detail so far. Instruments like the James Webb Space Telescope are designed not only to seek traces of biological life, but also to look for signs of technological activity. Astronomers suggest that with the tools we already possess evidence of a type, one civilization would likely have been detected within the regions of space we have surveyed. In that scenario, extraterrestrial craft would be moving through space at velocities that would make them difficult to miss. A Type 2 civilization would also struggle to remain completely invisible. To harvest sufficient energy, it would need to enclose stars within Dyson spheres. If such a structure were built at the same distance from its star as the Earth is from the Sun, and if it were stable, it would contain an interior surface area roughly 600 million times greater than that of our planet. In other words, the inner surface of a Dyson sphere would dwarf the entire surface area of the Earth. Estimates suggest that a megastructure with a radius of 1 astronomical unit would require around 10 to the 27 kilograms of material, approximately equal to the mass of Saturn. Even this figure assumes a solid shell and does not fully account for the immense technological challenges involved. Constructing such structures would demand vast quantities of material and energy, and turning stars dark by wrapping them in Dyson spheres would be an unmistakable signature. Nothing of this sort has yet been observed in the Milky Way. There have been moments of excitement, however, when scientists believed they might have glimpsed something similar. On one occasion, a powerful signal detected from the star HD 16495, located 92 light-years from Earth, was briefly thought to be the beacon of a Type 2 civilization, only to be later identified as a BIT, military satellite orbiting our own planet. In 2008, astronomers observed what appeared to be an exoplanet orbiting an unusually bright orange dwarf star, later named Fomalhaut b. Initially, it looked like a cold but luminous point of light moving rapidly across the sky. Yet by 2014, the object had disappeared, leaving researchers puzzled. Some proposed that the orbit had become unstable, allowing the object to drift away from its parent star. Others suggested it might have migrated to orbit a larger, brighter star elsewhere in the galaxy. Further investigation eventually revealed that the object was not a planet at all, but an enormous cloud of frozen debris. This cloud is thought to have formed from a rare and violent collision between two icy asteroids. While we may never know with certainty what truly happened to Fomalhaut b, one speculative idea is that a Type 2 civilization might have harvested material there to construct a new megastructure, such as a Dyson sphere. The mystery surrounding disappearing stars naturally raises a deeper question of how we would even begin to trace the activity of a Type 3 civilization. Civilizations at the 3rd level appear to be either extremely rare or entirely absent from our local universe. Astronomers have searched for them using the infrared telescope, WISE, expecting to detect vast amounts of infrared radiation that such advanced societies would emit. So far, no such signals have been found, though the search continues. One hypothesis suggests that a Type 3 civilization could be concealed within enormous cosmic voids, regions whose origins are still not fully understood. A notable example is the Boötes Void, an immense expanse, almost entirely empty of stars and galaxies. It spans about 330 million light-years in diameter, accounting for roughly 0.27% of the diameter of the observable universe. Some scientific speculation proposes that this apparent emptiness could in part be the result of activities carried out by an advanced Type 3 civilization. It is conceivable that some extraterrestrial societies have been quietly obscuring entire galaxies one after another, perhaps shrouding their stars within vast Dyson spheres or even relocating them to places of their choosing. Scientists hope that the steady march of Earth's technological progress will soon allow us to put such bold ideas to the test. Data gathered by NASA's Kepler Space Telescope indicates that roughly 20% of stars in the universe possess planets orbiting within their habitable zones. If these estimates are even approximately correct, then within the Milky Way alone, there could be around 20 billion stars capable of hosting planets with liquid water. Extend that reasoning to the entire universe, and the number of stars could reach as many as 1 septillion stars. Even the recently suggested age of the universe, 26.7 billion years, amounts to little more than a fleeting moment when set against the vast temporal backdrop of the cosmos. Stars like our own Sun enjoy lifespans of about 10 billion years, while other stars endure for trillions of years before exhausting their nuclear fuel. Black holes themselves would eventually fade away as well, though only long after every star has vanished. By the time the universe finally drifts toward heat death, 20 of years will have elapsed. Faced with such immense stretches of time, some scientists find it difficult to believe that humanity represents the only civilization ever to arise. Figuratively speaking, the universe appears rich with fertile soil regions where life has had billions of years to develop and will have even more time to emerge in ages yet to come. Recent advances in space exploration have already revealed intriguing hints of possible biomarkers on distant worlds. While the discovery of microbial life beyond Earth would be extraordinary, it is the prospect of an advanced and intelligent civilization hidden among the stars that truly captures our imagination. This leads to a profound question. Are we in fact the first spacefaring civilization in the entire universe? To approach an answer, scientists must consider a range of crucial factors, including the yearly birth rate of stars, how commonly those stars host planetary systems, how often habitable planets appear within their Goldilocks zone, the chances that life begins on such worlds, and the likelihood that life evolves into technologically advanced societies. All of these considerations are woven together in a single framework known as the Drake equation, first proposed in 1961. In the past, astronomers possessed only rough estimates of how frequently stars formed. Today, we are surrounded by data. More than 5,000 exoplanets have now been confirmed, with around 10,000 additional candidates awaiting verification. As our instruments grow more sophisticated and our understanding of the cosmos deepens, we continue to uncover an ever greater diversity of celestial bodies. Yet despite this abundance of information, many uncertainties remain, making it difficult to say whether civilizations like our own exist right now. To cut through this uncertainty, scientists refined the Drake equation and posed a simpler question. Have there ever been technologically advanced civilizations before us? The answer they arrived at was startling. Their calculations suggest that the probability of humanity being the only intelligent civilization that has ever existed is 1 in 10 billion trillion. It is akin to surveying 10 billion trillion stars and never once encountering a star like our Sunday. For much of history, our ancestors believed themselves unique and imagined Earth as the center of everything. We now know how mistaken that view was. The Copernican principle tells us that Earth, humanity, and our position in the universe are not special. In astronomy, this implies that vast regions of space should be broadly similar in their makeup. If the ingredients for life exist here, it is reasonable to suppose they exist elsewhere as well. In biology, this suggests that the physical processes that gave rise to life on Earth could mirror those that produce life beyond our planet. There is also the idea that because humanity exists at all, the laws of nature must allow for life to arise, an idea known as the anthropic principle. The universe appears remarkably suited to life. Protons bind together to form stable atoms, stars forge heavier elements, and release the energy upon which we depend, and even the fundamental constants of physics seem delicately balanced. When this perspective is combined with the Copernican principle, it leads us to suspect that life may emerge and fade repeatedly across the vast scale of the universe. This is rather like saying that if we stand here and observe trees growing around us, and we assume that our position is not in any way special, then the mere fact that these trees exist here suggests they must also exist elsewhere on Earth. By extension, there should be at least one region of the universe resembling our own, and given the sheer scale of the cosmos, that region could stretch across millions of light years. In our galaxy alone, there are more than 300 million planets with conditions similar to Earth. When this reasoning is applied to the Milky Way, estimates suggest there could be around 36 civilizations comparable to ours. Of course, this rests on a highly optimistic assumption, so the question becomes, what other methods might allow us to make a more grounded estimate? By simply considering the moment in cosmic history when humanity emerged, and by reflecting on how empty space appears to be, we can begin to construct projections about civilizations that may arise in the future, as well as speculate about those that might have existed before us. So how can we tell whether we are early or late in the grand timeline of the universe? If the rate at which civilizations appear is high, and most of them have already disappeared, then humanity would be arriving late to the cosmic story. But if this appearance rate is low, given the current age of the universe, then we may in fact be among the very first advanced civilizations to exist. Observations tell us that the majority of stars formed during the first few billion years after the universe began. At that time, heavy elements were scarce. These elements are forged in the cores of massive stars over their lifetimes, and scattered into space when those stars end their lives as supernova explosions. Because it was still too early for most stars to have exploded, very few rocky planets, if any, could form. Today, star formation is about 30 times lower than it was at its peak, which occurred when the universe was roughly 3 billion years old. Around 95.5% of stars have lifespans longer than that of our Sun, and if red dwarfs, which make up about 73% of stars in the Milky Way, can support suitable conditions on nearby exoplanets, then life is about 1,000 times more likely to emerge in the distant future than it is right now. Planets orbiting red dwarfs would have vastly more time for life to develop. In around 1 billion years, Earth will receive so much heat from the Sun that it will no longer be habitable. This means our planet provides roughly a 5 billion year window for life to emerge and advance. If astronomers are right about red dwarfs, these stars dramatically extend the time frame during which life could arise on surrounding exoplanets, suggesting that the universe may become increasingly hospitable as time moves forward. But life as we understand it does not begin as an advanced species. On Earth, it took nearly 1 billion years for life to originate, followed by an additional 3 billion years of evolution before humans developed technology. We do not know how quickly life typically progresses towards civilization because we only have a single example and nothing with which to compare it. One framework scientists use to approach this problem is known as the hard steps model. It is, in essence, a sequence of crucial milestones that must be passed for intelligent life to appear. These steps are called hard because they involve extraordinarily rare evolutionary transitions. This journey runs from the emergence of the simplest cells through the increasing complexity of life to the human brain and the eventual development of artificial intelligence. You can think of it as a chain of highly improbable events. Complex cells must arise from available biomolecules or perhaps from material delivered from space. Efficient systems of reproduction must develop. Living organisms must evolve ways to process information such as neurons. Consciousness must emerge, followed by the creation of technology. According to Andrew Watson, around 4 such hard steps were required for intelligent life to arise on Earth. What remains unknown is whether our path was typical and how many of these stages life elsewhere would need to traverse. If scientists can determine the number of these hard steps, they can use mathematical models to estimate how frequently life appears in the universe. And if the usual number of hard steps required to reach an advanced civilization is greater than the number humanity experienced, then it would suggest that we skipped some stages and that our arrival came surprisingly early. If we suppose that most extraterrestrial civilizations, at least within the Milky Way, have followed an evolutionary trajectory broadly comparable to our own and progressed at a similar pace, then they would likely have already developed interstellar probes. If such a civilization emerged even just 1 billion years earlier than humanity, it would have had sufficient time to traverse the entire galaxy, using technology that is already within our reach today. And yet, we see no sign of them. One scientific proposal addressing this mystery is known as the Grabby alien model, put forward as a possible explanation for the Fermi paradox. The idea suggests that these conspicuous expansion-driven civilizations arise more frequently in large galaxies and spread outward through the universe at a characteristic speed shaped by local conditions and the obstacles they encounter along the way. But what might that speed be? Given that we have not observed vast regions of space showing clear technological signatures, Scientists have inferred that such grabby civilizations would expand at roughly 50% of the speed of light. Simulations indicate that whether there is a single intelligent species or multiple loud civilizations, they could by now occupy around 40 to 50% of the universe, if expanding at that rate. Under these assumptions, humanity could encounter grabby aliens in something like 200 million to 2 billion years, assuming we persist for that long. This framework also helps explain why quieter civilizations would be far more difficult to detect. Their planets may already have been colonized, or perhaps potential intelligent life never had the opportunity to arise because grabby aliens arrived first, depending on where those planets lie within the universe. All of this imposes a kind of deadline on emerging life. It becomes a cosmic race between those that manage to navigate the demanding stages of evolution more quickly and those that simply benefit from an earlier start. If we further assume that noisy space claiming civilizations originate from quieter ones, then the probability of even a single quiet civilization currently operating within our galaxy would be extraordinarily small, less than 1 in 10, 000. Yet it is also possible that loud civilizations expand far more slowly. If, on average, civilizations arise at great distances from one another, they might choose their moments carefully waiting until their star system drifts closer to another as both orbit the galactic center. This is a strategy we already employ when planning interstellar missions, or even journeys within our own solar system. Researchers have also examined the possibility that Earth may have been visited in the distant past. An advanced civilization could have reached our planet 10 million years ago, or perhaps far earlier. Imagine that for a moment. They arrive with technology beyond anything we can conceive, yet as they explore our world, they find no evidence of intelligent life, no trace of civilization as we understand it today. They might simply have departed to continue exploring the galaxy, or perhaps they chose not to interfere with the natural course of evolution, allowing us the time to develop. After all, we humans also make efforts not to disrupt the lives of certain tribes that remain untouched by modern technology even now. There are countless possible scenarios for the past, present, and future existence of intelligent civilizations, and for now, we can do little more than speculate. Theories and models allow us to make estimates and assess probabilities using the variables currently available to us. We have advanced mathematics to the point where we can solve equations with 1 or 2 unknowns given only a few parameters. But when we attempt to tackle problems involving 5, 1, 0 or more unknowns, the complexity grows dramatically and the range of possible outcomes becomes vast. At present, empirical evidence suggests that humanity may sit relatively early in the history of the universe and that many more civilizations could emerge long after we are gone. Still, all it would take is a single breakthrough to overturn this perspective entirely. Humanity may need to be fortunate once again, taking another crucial hard step forward. That step could be the creation of a new kind of technology capable of precisely scanning star systems and galaxies across the entire observable horizon. Such a revelation might be closer than we think. Quantum computers and artificial general intelligence, once realized, could evolve at an exponential pace, potentially delivering more knowledge in short spans of time than all of humanity has accumulated throughout its entire existence. The question that remains is whether we are truly prepared to confront the answers we have been seeking for so long. Scientists also propose that if alien life does exist, it is likely to be based on carbon as its fundamental building block. Since the universe is composed of the same chemical elements everywhere, it is plausible that the underlying recipe for creating life in all its diverse forms is universal. Carbon sits at the heart of every biological molecule we know. Its remarkable ability to form stable bonds with 4 other atoms allows nature to build long molecular chains and exquisitely complex structures. From this simple versatility arise proteins and DNA, the essential machinery that enables life to function. Yet the presence of carbon-based life elsewhere in the universe would not mean a simple copy of what we see on Earth. Even subtle differences in environment can steer evolution toward forms of life that are profoundly unfamiliar. Imagine comparing Earth's gravity with that of a distant alien world. If the gravity on an exoplanet were far stronger than ours, blood would be drawn relentlessly into our legs, bones could fracture under our own weight, and we might find ourselves pressed helplessly against the ground, unable to move. Creatures native to such a planet would almost certainly evolve stout, compact bodies, forms built for strength and stability in the face of an overwhelming downward pull. Thick and robust skeletons, perhaps supported by natural armor like coverings, would help them bear their weight. These features would counter the constant force of gravity and reduce the risk of structural damage in such an extreme environment. Life in these conditions would most likely cling to the planet's surface or retreat beneath it. Surface or underground dwelling organisms might develop specialized limbs or gripping structures to anchor themselves firmly, ensuring balance and stability. Movement would be slow and deliberate, a careful negotiation with gravity itself. Crawling or rolling could become common modes of locomotion, as they offer greater steadiness and reduce the chance of injury. Some species might evolve multiple limbs or appendages, spreading their mass more evenly and improving their ability to move across the terrain, though every motion would demand significant energy and effort. Now consider the opposite extreme. On a world with much weaker gravity, small and agile creatures would experience a dramatic freedom of motion. They could leap farther, accelerate faster, and even fly with far greater ease than anything on Earth. In such places, one might imagine enormous insects, butterflies the size of hawks, or birds larger than airplanes inhabiting an alien sky. If this planet followed a highly elongated orbit around its star, seasonal changes would be extraordinarily harsh. During unfavorable periods, its inhabitants might enter deep hibernation or a state of suspended activity, much like the hibernating animals we know on Earth. On planets far from their host stars, where light is scarce and dim, the eyes of living creatures would naturally tend to grow larger. This would allow them to gather as much faint light as possible, making sense of their surroundings in the gloom. In contrast, worlds bathed in intense starlight would impose very different evolutionary pressures. Here, smaller eyes protected by thick eyelids would be favored, shielding delicate tissues from overwhelming brightness and allowing vision to remain effective under relentless illumination. The idea of life surviving on planets without a protective magnetic field exposed directly to lethal radiation may seem difficult to accept. Yet scientists suggest that even these harsh conditions might be navigable. Some organisms could adapt in extraordinary ways, potentially drawing energy directly from cosmic radiation. Intense radiation at the surface could even become a resource for small life forms, which might shelter underground and emerge only to gather the energy and nutrients they need. On a highly molten planet where liquid water is unlikely to exist, carbon chemistry may struggle to operate at all. Carbon relies on interactions with water to build the organic molecules essential for life. In such environments, other elements may take center stage. Silicon, which shares carbon's ability to form multiple bonds and a wide variety of molecular structures, is often proposed as an alternative foundation for life. However, at temperatures typical of Earth's surface, silicon is far less reactive than carbon, making it less suitable for the rich and intricate chemistry life requires. As we continue to discover more exoplanets, some of them unimaginably hot, the possibility of silicon-based life attracts increasing attention. One such world, known as GJ 1252b, lies just 65 light-years away. It orbits extremely close to its star, enduring searing temperatures that define a truly extreme environment. It is entirely reasonable to imagine the existence of unfamiliar forms of life, entities, unlike anything we encounter on Earth, perhaps living rocks or crystalline organisms. If silicon-based life forms do exist, they may find chemical environments such as liquid ammonia or methane far more hospitable than water. Yet high temperatures would present a serious obstacle because these substances would readily evaporate. One fascinating alternative is sulfuric acid, a substance hazardous to human skin, eyes, lungs, and teeth. In the year 2022, scientists from the Massachusetts Institute of Technology revealed that sulfuric acid can promote the formation of a wide range of organic compounds built around silicon. Remarkably, sulfuric acid remains liquid at temperatures exceeding 300 degrees Celsius. The clouds of Venus are rich in aerosol droplets of sulfuric acid, suggesting that this planet could offer a surprisingly stable environment for silicon-based microbes. Under these extraordinary conditions, silicon may rival carbon as a fundamental ingredient for life on a cosmic scale. But what might occur if these elements were combined and encouraged to function together as a unified system? Many researchers see silicon and carbon as an exceptionally promising partnership. Even on Earth, we observe examples that hint at this potential. Diatoms, a form of algae, construct silicon-based shells, while single-celled organisms known as radiolarians possess skeletons made of silicon. More recently, scientists have uncovered a new way to persuade living organisms to chemically bond carbon and silicon. This was achieved through a method known as directed evolution, in which microbes are steered to generate entirely new molecules by concentrating on enzymes, the proteins responsible for driving chemical reactions. By imitating nature's own strategy of evolving enzymes through mutation, researchers produced a mutant enzyme capable of creating more than 20 distinct organosilicon compounds, 19 of which were completely unknown to science. The experiment demonstrated that this enzyme could synthesize organosilicon compounds in a controlled setting such as a test tube. Beyond that, scientists genetically modified Escherichia coli bacteria to manufacture the mutant enzyme within their own cells, enabling the bacteria themselves to produce organosilicon compounds. If forging links between silicon and carbon can be accomplished so readily in the laboratory, it is entirely plausible that nature achieved the same feat somewhere else in the universe, or perhaps selected an entirely different chemical foundation for life. Boron, for instance, has attracted considerable interest among researchers because of its remarkable properties surpassed only by carbon. Boron exhibits an extraordinary range of chemical behaviors, and among its most intriguing compounds are boranes, which can incorporate up to 12 boron atoms. The complex structures of boranes could potentially support the emergence of life, or drive intense chemical reactions, as they are known for their extreme reactivity. Diborane gas, for example, can ignite spontaneously upon contact with air or water. For boron-based life to thrive, an environment lacking atmospheric oxygen, seas and oceans would be essential. Furthermore, only an exceptionally cold planet would provide suitable conditions, and if such organisms were warm-blooded, they might require thick skin or dense fur to survive. Unlike boron, which is relatively scarce across the cosmos, metals are far more abundant. Astronomers have identified several worlds rich in iron. Mercury, for example, contains an unusually high proportion of metals. The exoplanet GJ 367b in the constellation Vela appears to be composed almost entirely of iron. Another world, the exoplanet WASP 121b in the constellation Puppis, is thought to host clouds of metallic vapor, where instead of water, rain, liquid rubies and sapphires may fall from the sky. For a moment then, it is worth contemplating the possibility of metallic life on such planets. A researcher from the University of Glasgow has successfully created living cells from a rare metal known as tungsten or wolfram. Under ordinary conditions, this element is a solid, heavy, shiny metal with a silver-grey appearance. The results showed that these cells can selectively permit certain chemical substances to pass through, while blocking others closely, mirroring the role played by the membranes of organic cells in determining what enters and exits. The idea of a hypothetical form of metallic life presents a profound challenge to our understanding of biology. Scientists have speculated that such beings, if they exist, would display extraordinary resilience, perhaps even appearing almost bulletproof within the immense emptiness of space. Life, after all, may take shapes far beyond our expectations, built from elements we would normally consider hostile or toxic. As strange as it sounds, researchers are seriously exploring the possibility of life forms that rely primarily on arsenic-based biochemistry. The foundation of this idea rests on the fact that arsenic can, under certain conditions, take the place of phosphorus within molecules that form the essential building blocks found in every cell of the human body. Chemically speaking, these two elements share striking similarities. There is even a hypothesis proposing that the earliest life on Earth may once have used arsenic instead of phosphorus in the structure of its DNA. Even today, some marine algae continue to incorporate arsenic into complex organic compounds as part of their biology. More recently, an extraordinary discovery emerged from an astrobiology research program where scientists identified the first known microorganism on Earth capable of reproducing using arsenic. This unusual bacterium, known as GFAJ1, was discovered living in the harsh environment of Mono Lake in California. GFAJ1 appears to replace phosphorus with arsenic in its DNA and in other critical cellular structures. While researchers emphasize that further investigation is required before drawing absolute conclusions, this finding strongly suggests that nature may be capable of integrating arsenic into the biochemistry of organisms beyond our planet. It may simply be that a civilization like ours is still too young to fully grasp the diverse strategies nature can employ. Fossil evidence of microorganisms tells us that life emerged very early in Earth's history, yet exactly how and where this process began remains one of science's greatest mysteries. Living organisms are extraordinarily complex, built upon delicate networks of genes and molecules. This presents a puzzle because even the simplest bacterial cell contains hundreds of genes and thousands of different molecular components. Some scientists propose that before genes existed and before cell walls took shape, the earliest requirement for life may have been a metabolic engine, Metabolism lies at the heart of all living systems, and many researchers believe it formed the core of the first living cells. Once such engines were initiated, they could generate the chemical ingredients necessary for life, eventually leading to the spontaneous assembly of cells themselves. Yet metabolism is an immensely complex process, raising a fundamental question. Did the chemical engine responsible for building cells come first, or did cellular structures need to exist in order to create that engine? In a remarkable experiment designed to explore this mystery, scientists combined 12 chemicals in water that participate in a process known as glycolysis. They heated this mixture to conditions thought to resemble those near an undersea volcano, maintaining a temperature of 70 degrees Celsius for 5 hours. To further recreate the ancient ocean environment, the researchers added elements such as iron and sodium substances believed to have been abundant at the time. Iron in particular was found to significantly enhance the chemical reactions. After several years of persistent experimentation, the scientists succeeded in producing a network of 28 functioning reactions, including a complete metabolic cycle. Life is unimaginably diverse, and metabolism represents just one of many possible mechanisms that might drive its emergence. It is entirely possible that metabolism is only one pathway among countless others guiding life into existence. Somewhere within the vast cosmic expanse, there may be numerous parallel routes, each governed by its own intricate chemistry together, forming a grand symphony of life that we are only beginning to hear. Recent studies have shown that inorganic grains made of iron, silicon, magnesium, and carbon can display remarkably lifelike behavior when immersed in plasma under particular conditions. These particles are able to assemble into complex compounds, allowing interactions that closely resemble those we usually associate with organic matter. For a long time, scientists assumed that solid particles drifting through cosmic plasma could form nothing more than simple thread-like filaments. Yet, with the help of advanced computer modeling, something far more intriguing has come into view. These filamentary structures can spontaneously organize themselves into spiral and helical forms, guided purely by self-organization. Even more striking is the discovery that such formations can interact with one another and undergo transformations reminiscent of the processes seen in DNA and proteins. These enigmatic helices and spirals, built entirely from solid particles, are capable of dividing or replicating, producing two copies of the original structure. Through their mutual interactions, they change, adapt, and evolve. Within the plasma environment, the most stable and well-adapted forms persist, while the less stable ones fade away. Somewhere in the vastness of the universe, there could be a living helix drifting within a cosmic plasma cloud, slowly evolving toward greater complexity. Or perhaps there exist nanometer-scale microbes clinging to the surface of a neutron star. Such hypothetical beings would not be composed of ordinary atoms but of densely packed nuclei forming nuclear molecules. Their existence would be fleeting, driven by rapid nuclear reactions. If they were real, their lifespans would last only a few minutes, and they would be detectable only under a microscope. Now let us turn the perspective around. What if there are colossal entities in the cosmos observing us in the same way we observe microbes through a powerful microscope? How large might such beings be? Perhaps the size of elephants, or vastly greater, spanning an entire ocean, a planet, a galaxy, or even a cluster of galaxies. It is conceivable that they could encompass the whole universe itself. Life then may not be confined to atoms and molecules alone, but could be deeply woven into the very fabric of the cosmos. In this view, life is everywhere, existing seamlessly all around us. It is an idea that challenges our assumptions and invites us to reflect on the profound nature of life within the grand scale of the universe.